Righto, some more fun with polynomials here. So let's have a look at example 1. All right, so in this lesson, we're just going to be looking at some factorizing some polynomials using what we've learned about long division, synthetic division, etc., and the remainder theorem. And we're going to use all that stuff to factorize. Look at this. This is a quartic. A product of linear factors. So we're going to factorize this guy, and then we're not going to check our answer. We might just then look at it on Desmos and see how that plays out. But this is pretty exciting territory because so far you've dealt with quadratics, you've factorized quadratics, and you've graphed them and done some things with those with quadratics. Familiar with that, but this is new territory. But because of what we've built up over the last few days and some of the skills we've built up, we're going to put all that together to help us with polynomials, well in this case of degree 4. So right, so just a little reminder that the remainder theorem, remember the remainder theorem, you probably can't see yellow, so I might go for a different color. Right, the remainder theorem, in a nutshell, the remainder theorem said that the remainder will be equal to P of A when P of X is divided by X minus A. Okay, does that sound okay? And then as a corollary, the factor theorem, well, it states that if the value of the polynomial at A is equal to 0, then X minus A is a factor. Right, and we're going to use that straight off the bat here with this question, right? Because we need a starting point in order to get going with this thing and start to break it down from a quartic to a cubic to a quadratic. I need to know what to divide it by, such that what I do, I'm not just going to pick any old value of X minus A. I want to pick one that I know will factorize it, lead to a remainder of 0. So there's no other way other than to get in there and guess and check and find out, oh, actually, I've just noticed X is a common factor here, isn't it? So we can break it back down to a cubic straight away. So let's start on this thing. We get an X out straight away, can't we? So it's X cubed minus 6X squared minus 19X plus 24. So that's a good little reminder there that you pull out common factors immediately. That simplifies matters. All right, we're down to a cubic now. So what I need a starting point. I don't have a cubic factorization technique like I do with quadratics, but this is it, right? I do now, and it's a guess and refined sort of approach. I'm looking to replace X with a number such that this polynomial will bring me to 0, because then I've got a factor of X minus whatever that number was. So I'm looking for this A, this magical A. Well, I know I will start with 1, but if 1 and negative 1 don't work, I'm going to take factors of 24. Reason being, when this thing's all factorized out, all my constant terms, which will sit on the back here, they're going to multiply to 24. So factors of 24 only, please. Don't go checking things like 5 or 1, 2, 3. 24 is pretty factor rich. So hopefully we're going to stumble across it eventually. So we're going to check. Right, we're going to check for we're going to check f of 1. Right, so this is a guess and refine approach. A guess and refine approach, right? So we start with f always start with 1, right? You never know. I'm not going to bother with this because it's just got 1 time. It doesn't matter. I need to make this cubic. I need to make that equal to 0. So it's 1 cubed minus 6 times 1 minus 19 times 1 plus 24. Right, now that's equal to, right, what's that equal to? That's equal to 1 minus 6 minus 19 plus 24. 1 minus 6, that's minus 5 minus 19 plus 24. I reckon we got ourselves 0. We're straight in. So that means, go back to our factor theorem, if PA equals 0, well, I've got P1 equal to 0 in this case, then x minus 1 is a factor. So therefore I can triumphantly state that x minus 1 is a factor, right? Because f of 1 is my 0 of x minus 1. All right, so now I can go into what? I know it's a factor, so I can divide it into my dividend, into my cubic. So how do I do that? Well, I can do it the fast way or the slow way. It's a linear, so I can use synthetic. All right, so let's use synthetic division. All right, so when we use synthetic division, we go with the upside down long division guy. We whack in here my divisor, my 0, sorry. And into here I whack in my coefficients. So I've got 1, -6, -19, and 24. A second line of attack here. 1 drags straight down, 1 times 1 is 1, add, multiply, add, multiply, lo and behold, 0, magical 0. So 0 remainder implies that x minus 1 is a factor. X minus 1 is a factor. We knew that already, but we got there. And what we wanted to do, though, we wanted to know what resulted when we divided by x minus 1. Well, this is what resulted. So we can therefore say that my fx equals, well, I took x out to start with. Now I've taken x minus 1 out, and I'm left with a quadratic now, aren't I? X squared minus 5x minus 24, and it's plus 0, but we don't need to worry about writing plus 0. Right, now, what does this get us? X minus 1, I'm good with quadratics, and especially ones that look like this. This looks like -8 and plus 3. So I reckon that's my factorized cubic, quartic. X minus 1, x minus 8, x plus 3. If I wanted to graph this now, I would have it would look like this. Right, it's a quartic. I've got 4 points of intersection. All right, they're at -3. 1, 2, 3, right there. All right, that's 1. They're at the next one I'm going to arrive at is 0. Then I'm going to arrive at 1. And the last one is at 8, all the way over here. Now, which way is it? I'm going to pass through. So I've got all 4 real roots. I'm not going to, these are called roots or solutions. I'm not always going to get 4 for a quartic, but I am going to get a combination of real and complex solutions. I'm going to get 4 of them. So I'll repeat that. I'm going to get 4 solutions for a quartic. Now they're not all going to be real. They might be a combination of real and complex. So for 4 roots, well, we can't just have one complex root. We've got to have 2, and we'll look at that in a moment when we have a look at some complex solutions. But for this one, I've got 4 real solutions. Now, how do I graph it? Well, the end game for this one, because it's an x to the power of 4, and it's positive x to the power of 4, the end game is going to look like this. Right? It's going to be shooting off in this direction here, right? Because as the most powerful term, as the leading term, it's going to take over. It's going to dictate. So because it's positive, it's going to be increasing. So, but in around the x-axis, there's going to be some movement, and it's going to be something like this. Now, what else do I know about this thing? I've got a y-intercept that I need to represent. It's it's 0, isn't it? It's bang in there at the root. So I tend to work from right to left with these because I know how it's going to end up. So I'm just backtracking, and apologies for my sketching abilities or lack of. And so it's going to look something like that. This is my function of x, y. This is f of x. That's my polynomial. Let's put in -3, 0, 1, and 8 as my roots. Once we've done some work in some calculus, we'll be able to work out what these turning points are, and that'll be fun. But for now, that'll do us. Let's get on with the next example. Okay, and we continue to go up in the world here. Look at this. I've got -1 is a 0, of this polynomial. Now it's a power 5. It's a degree 5 polynomial. Wow. Let's check this thing out. We've got 1, 2, 3, 4. We've got 6 terms, so they're all covered. -6, that's my constant term. I'm already thinking that's my y-intercept. Multiplicity 3. Oh, okay. Here's a new term. What does this mean? Multiplicity 3. All right, I'll tell you what it means. It means that this -1 is a triple zero. All right, that's a triple zero. So -1 is a triple, right? Triple zero. Okay, so what that means is, all right, so if I've, for example, x minus 1 cubed, if this is my polynomial, then that's a triple zero. All right, I've got 3 zeros and they're all the same. 1, 1, and 1. And we do say we've got 3 zeros, even though they're equal, we say that we've got 3 zeros. That's why we use, when we're talking about the discriminant, why we use the word distinct roots, because when we've got 2 equal roots, we don't say that's one root, we say it's 2 equal. So that's just to highlight the fact that we're looking for the total, we're looking for all the solutions. And for a power 5, we're looking for 5 solutions here. We're looking for combinations of, now they're not always going to be real solutions. In fact, quite often you'll have a combination of real and complex. And complex solutions, they come in pairs. More about that later. So that just means that this guy runs through 3 times. So I'm going to go through and probably do a synthetic division, I would have thought, and just bring this guy back. Once I've done it once, it'll be a power 4. Once I've done it twice, it'll be a power 3. Once I've done it 3 times, it'll be a quadratic, and I'm in my comfort zone there. So, right, let's go. Synthetic, I'm in synthetic territory here. You can times 2 me, because I'm just going to be going synthetic, synthetic, synthetic through 3 operations with this. So, all right, bear with me. So I put my 0 down here, my upside down. All right, what you should be doing really is pausing and doing this, because you're good at synthetic by now. Remember, we're doing this operation of -1, we're doing it 3 times. Sorry, -1 is a 0. I'm sorry, -1 is a 0. That means, what does that mean? That means that x plus 1 is a factor. All right, we have to translate all the time. All right, so -1 goes in, and off we go. 2, 7, 3, -13, -17, -6. 2 drops in here. 2 times -1 is -2. 5 drops in here. -5 goes there. -2 in here. +2 there. -11 here. 11 there. What are we up to? -6, 6. Fantastic. 0. Okay, different color now, please, because I'm going to use these on -1 again. All right, obviously I'm not going to bother with that guy, but -1 goes in here, and this is my second 0 of -1. 2 drops in here. 2 times -1 is -2. Add. Multiply. Add. Multiply. Add. Multiply, add. All right, that's 3. 1 more to go. So I'm going to use these now, and I'm going to go into green on my third. Bring the 2 down. Multiply, add. Multiply, add. Multiply, add. Satisfying zeros are popping up here. So what does this mean? I've done 3 x minus 1s, minus x plus 1s, and now I've got, so right, so let's what do we got here? Fx. Let's just summarize what we've got so far. Fx equals, I've got a triple root at -1, so multiplicity 3, remember, a triple 0. So that's a cubic, x plus 1 cubed, and what's left? Well, what's left is 2x squared, right? I've got a cubic here multiplied by a squared. That brings me back to my 5. Always be checking that sort of stuff. 2x squared plus x minus 6. I've got plus 0 here, but don't be silly. You're not writing that out. So what do we got? We've got x plus 1 cubed. 2x squared plus x minus 6. what do we get from that? We get, all right, we're getting two numbers that multiply to negative 12 and add to 1. So that would be 4 and negative 3. So I end up with 2x squared plus 4x minus 3x minus 6. That's going in there. Just bear with my factorization here, because this is the way I like to do it. 2x, x plus 2 in there, minus 3, x plus 2 in there. Okay, I'm just about there. Cubic, and I've got 2x minus 3, x plus 2. Right, there are my 3, 4, 5 factors. Multiplicity 3, and then singles. Okay, right, again, let's draw a pretty little picture here. We've got 5 roots to represent. They're all real roots, but there's a triple here at negative 1. So let's get him into position right there. What else have I got? I've got a single at negative 2, and I've got a single at 1.5. All right, about there. All right, how do I do this? Right now, again, I work from the right, don't I? So I've got 2x to the power of 5, so I am heading off in that direction there. So back I come. This is a single, so I'm straight through. Oh yeah, where's my y-intercept? Y-intercept's at negative 6. So wherever, I'm going to pass through negative 6 here. But right, this is, what's this, 3 over 2 here? Here's my negative 1. I've got to have a triple here. Now the way I represent a triple is by doing something like that through the axis. It's like a little point of inflection through there. A little shimmy around. Turns around, comes back, and right through 2. How am I going here? That's negative 2, I'm sorry. Negative 2, and this here is negative 1, but I just get that little effect through there to account for the triple. I better do all my bits and pieces so that here's my f of x polynomial in graphical format. All right, next one. Okay, something different for you here. We've got a cubic, right? We've got a cubic here, but look at this. This is the biggie. 1 plus 3i is a complex 0. You bet it's a complex 0. So now we're starting to look at, oh, okay, no, I don't have all real zeros here. I've got a cubic. I can expect 3 roots, 3 solutions. One of them is complex. Now, I mentioned a minute ago, complex zeros complex solutions come in pairs. Right, so it's called the conjugate root theorem. Right, we better talk about it. The conjugate root theorem. And it simply says this. It says that if I've got a complex root, right, so what it says is, it says that if a polynomial has a complex 0 z, right, so if a polynomial has a complex 0 z, say, then z star, the conjugate of z, is also a 0 of the polynomial. Right, so if a polynomial has a complex 0 z, then z star, right, the conjugate of z, is also a 0 of the polynomial. All right, better write that down. That's important. So that means, so therefore, with this question, with this example, therefore, if 1 plus 3i is a 0 of f of x, right, then 1 minus 3i is also a 0. All right, that's what it implies. So let's check this out. All right, 1 plus 3i. Given that 1 plus 3i is a complex 0, well, let's not take their word for it. Let's check it. If it is a 0, then I'll be able to sub it in here for x, and I should get 0. Right? Isn't that the point of a 0? It's the value of x that gives you 0. So let's just check. Let's be suspicious here. So check. Right, so what I should get is that 1 plus 3i cubed minus 5 by 1 plus 3i squared plus 16 by 1 plus 3i minus 30. Right, I'm gonna evaluate this. I should get 0. Okay, so this is a cubic, therefore, so this cubic, so I'm going to use the binomial theorem to help me out with this one. Right, I'm going to have 1, right, then I'm going to have 3 by 3i, then I'm going to have 3 by 3i squared, then I'm going to have 3i cubed. All right, this is going to be long and gross. 1 plus 3i is going to be 1 plus 6i plus, all right, so now 9i squared, so it's actually minus 9 in there. All right, now I've got plus 16 plus 48i minus 30. Okay, this is live TV, folks, so there could be errors everywhere. I'm willing to take that on. Let's see what we got here. Maybe you're pausing and getting ahead of the game. That'd be excellent too. 1 plus 9i plus, hey, we're not going to do this every time, are we? We're just checking. This is the first time we've come across a complex 0. Just going to show you that it works the same way as any other 0, that you plug it in, you get 0. Then we'll deal with the conjugate of z. Okay, 3i squared, 9i squared, that's minus 9. Cool. Minus 9 times 3 is minus 27, so I better get a minus 27 in there. Hopefully I got that right. This says 3i cubed, so that's 27. Don't forget, that's 27i cubed. Now I squared is minus 1, so that's going to make it minus 27, and then the I pops on the end. So it'll be minus 27i, I hope. Minus 5, minus 30i, plus 45, plus 16, plus 48i, minus 30. Oh my word. Okay, so I've got some real and I've got some imaginary, and I'm hoping I get 0 for both. Right, so let's have a look at the real. I've got 1 minus 27, so I'm on minus 26. Minus 31, right? Oh, hang on, plus 45, so I'm back into the positive, and I'm at 14. Add 16, I'm at 30. Sigh of relief, I get 0. All right, let's check now with my imaginary. 9i. Minus 9 minus 27 is negative 18. Oh, I'm at negative 48. Oh, plus 48. 0i. So 1 plus 3i, that's a root. Now what the conjugate root theorem says is that if we replace with 1 minus 3i, I'm also going to get a root. So if 1 plus 3i works, 1 minus 3i is going to work. So let's just do a little, let's just go in here and change here. Oh, didn't work, did it? So I'm going to change all my 1 pluses to 1 minus. 1 plus to 1 minus. This doesn't prove anything, but it just shows, it'll just show that it also works. So what changes in here? All right, I've got a minus 3i in here. I've got a minus 3i in here. All right, so all these little pieces just change. I've got minus 5 by 1. That'll be minus 6i. Does the negative 9 change? I don't think so because of the squaring business. So it'll become minus 3, so it's still plus 9i squared, so minus 9. And I will get a minus 48i here. I think everything else is the same. So what will change in here will be a negative 9i. What will change in here is not much at all because I'm squaring negative 3i. It's the same as squaring 3i, so that's going to stay. Now this is going to change. I'm going to have negative 27i squared, so it gives me plus 27. So that'll change to plus 27i. Minus 5 there, I get a plus 30i here. And I get a plus 45, plus 16, minus 48i. But you can see what happened. There were some sign changes. Let's see now in red what we get. 1, has anything changed in the red? 1 minus 27. Where are we now? Minus 26, minus 31, 14, 30, minus 30, still 0. Now look at the yellow, negative 9i plus 27, so I'm now at positive 18, positive 48, minus 48, still 0. So we can see there by checking that if 1 plus 3i works, which it does, then 1 minus 3i is also going to work. So that means I've got 2 zeros. If I've got, you get 2 for 1 here. You get 1 complex, you get another. So 1 plus 3i and 1 minus 3i are both roots. All right, so let's just make a note of that. Therefore, 1 plus 3i and 1 minus 3i are zeros of fx. Beautiful. I've got 2 done. It's a cubic. I've only got 1 more. So how are we going to find it? Well, if they're zeros, then we can say therefore that x minus 1 plus 3i, right, that guy, and x minus 1 minus 3i, we can say therefore that those guys are factors of fx. Does that make sense? So if if I know that 2 is a 0, then I know that x minus 2 is a factor. Right? That's all I'm saying here. So if they're factors, that means that multiplying them together, well, if I multiply them together, and then take my dividend and divide by what I get here, I should get my remaining factor. What do you think? Let's see how we go. So therefore, if I multiply these two factors together, does that seem like a reasonable thing to do? Well, it is. X squared, in case you're wondering. Now, x by minus, all right, so this is now looking a bit dodgy. I might need to run this out into a 3 by 3. All right, so instead of, what I figure here is instead of, so if I expand, so I take the inner brackets out, I end up with x minus 1 minus 3i, and I end up here with x minus 1 plus 3i, and this looks a little bit to me like, can I work it so that I've got conjugates here? Is that a conjugate product? X minus 1 minus 3i, x minus 1 plus 3i. I know what happens here, and I can do that bracket, right, because I work from left to right. I haven't changed the order of operations. So therefore, what I've got here, if I do this expansion, is with conjugate products, I know that I'll get x minus 1 squared minus, oh, that's a weird 2, minus 3i squared, right? Because this is just like saying x plus y, x minus y, and that results in x squared minus y squared. So that's all I'm doing here. It just looks a bit different, but this is what I'm getting at is that this is a quick expansion. Now x squared minus 2x plus 1. Now I'm subtracting 9i squared, which is subtracting negative 9. So I'm actually adding 9. So I get x squared minus 2x plus 10. All right, what is that? Well, that's the product of my two conjugate factors, if you like. So my two conjugate factors, my two complex factors. So that is what's left over. So my single real solution, and it must be a single real solution now. I can't get a complex one because complexes come in pairs and there's only one left. Now I divide my quadratic into x cubed minus 5x squared plus 16x minus 30, and we will have our linear. So we're going into, what are we going into? A long division because it's a quadratic divisor. So I'll just change my color of pen. So I'm going to go x squared minus 2x plus 10, and I'm going to divide that into my cubic, x cubed minus 5x squared plus 16x minus 5x squared plus 16x, and I don't want to get a sign wrong, that's why I keep going back up, minus 30. Okay, so let's do this division. X by x squared gets me the x cubed, it also gets me 2x squared, it also gets me plus 10x. Subtract negative 3x squared plus 6x down here. I put a minus 3 down, I get minus, I better bring my minus 30 down. Negative 3x squared plus 6x minus 30. Look at that. 0 remainder. So therefore, my f of x is equal to, well, in factored form, it's x minus 1 plus 3i. 1 plus 3i, that's one of my zeros. X minus 1 minus 3i. Oops. 1 minus 3i. And x minus 3. Now the product of those two gave me those two there. That product led to that quadratic, which on division gave me my final factor. So my question calls for, let's go back up to the question, given that 1 plus 3i is a complex root, find all the other zeros of f. So the other zeros of f are 1 minus 3i, right, the conjugate, and 3. So I better answer the question, hadn't I? Therefore, the other zeros of f of x are, what was it, 1 minus 3i, the conjugate of 1 plus 3i, and 3 was the real one, wasn't it? That's the real 0. Now, all right, so I've just graphed this in Desmos. Let's have a look at this. All right, there it is. So you can see in here, you can see 3 is the real 0, but you can see it's the only one, right? The complex zeros obviously can't be represented here on a real plane, but that's my cubic. You can see the cubic kind of shape to it, and there we have it. Okay, let's go to final example, and it's a beauty. And I'd love you to have a go at it, but feel free also just to watch this one out, and then you'll have opportunity to practice in the exercise, which is 3L, which we'll do 3 to 6. But let's do this example together. All right, so let's everything we've picked up is all going to culminate in a triumphant example 4. I can see it. All right, look at this. We've got a power 4. Cool. I've got 1, 2, 3, 4. I've got 5. Oh, hang on a sec. I've got an A here. Something's going on. I've got all terms represented. I've got a constant term of negative 24. That means what? It means that's my y-intercept. It's x to the power 4. It's shooting upwards at the end game. A is a real number. Take all the information in. Really important to be thorough when you read questions. Now, part A says find the value of A given that 2i is a complex zero of f. So we know that if 2i is a complex zero, what's the other complex zero? Remember, complexes come in pairs. So complex zeros come in conjugate pairs, right? They're very social. They can't go alone, the old complex zero. So therefore, what that tells me that if 2i is a 0, right, then what's its conjugate? Well, 2i, right, 2i is 0. Right, if I wrote that as a z equals, it would be 0 plus 2i, wouldn't it? So the conjugate 0 is 0 minus 2i. So negative 2i is another 0, right? It's a bonus. It's a 2 for 1 again. We know that 2i leads to minus 2i being a 0. So, all right, but it doesn't ask us that. It says find the value of a given that the 2i is a complex zero of f. Well, if 2i is a complex zero, that means I can substitute it in for x, and I'm going to get 0. So let's do that. Right, so in part A, I know that, actually, I hope you didn't go away and do this question. I went and did this, and it didn't work. And that's because there should be a 2 there. I think it should be 2x to the power 4. Right, so let's do this. So twice, all right, I'm going to put 2i in here. And what I should get if I put 2i in everywhere I see an x, I should get 0. But you see I've got a little a there. This is going to be 2i a minus 24, that all has to equal 0. Why? Because we're told that 2i is a complex 0. Righto, let's do this. Twice, what's this? 16i to the power of 4. Now, I to the power of 4 is the square of I squared. I squared is negative 1. Square of negative 1 is 1. 16 is the result. All right, this is, what's in here? There's an 8. Now, I squared is negative 1. So that's going to make it negative 8. And then there's an I hanging off. 2i squared, right, I've got twice. Right, this is 4i squared, and I squared is negative 1. So that's going to be negative 4. All right, and then things ease up a little bit, and I've got this. All right, so therefore, I've got 32 here. I've got plus 8i here. I've got minus 8 here. I've got 2ia here. I've got negative 24. All that's got to come to 0. Now, 32 minus 8 is 24 minus 24 is 0. So the reals cancel themselves out. So I've just got 8i plus 2ia equaling 0. So therefore, well, a is going to have to equal negative 8i over 2i. All right, and that is equal to negative 4. Okay, we're getting somewhere here, aren't we? We've got a equal to negative 4. That now goes into my polynomial, and we can work on that. 2i and negative 2i are zeros. So I know, therefore, I can write this. I'm going to have x, 2i is one of my factors. X plus 2i has to be another one, right? Because 2i and negative 2i are zeros. And that's going to leave some qx plus my remainder. Okay, so we want to find out, this now becomes our focus, qx. How are we going to get it? Well, I've got a quartic polynomial here, and I've got some complex zeros which I can expand and then take the result and use that as my divisor into my dividend to find out what qx is. Sound like a plan? So let's do that. So I'm going to rewrite this as, I don't know why I've changed color. Righto, so what do we got here? X squared. Again, look at this as a conjugate. So I love multiplying conjugates out. I know that 2 of my 4 terms cancel each other out. So I end up with minus 4i squared. I squared is negative 1, so it's going to be x squared plus 4. X squared plus 4 by some qx plus some rx, which I suspect is going to be 0, but we're going to allow for it. Okay, so how do I get my qx? So I'm going to take, it's a quadratic, my divisor is a quadratic, so I can't use synthetic. I'm going to have to go to long division, aren't I? Here we go. So 2x to the power of 4 minus x cubed plus 2x squared minus 4x minus 24, and that's divided by x squared plus 4. Great. Right, why don't you do this division and then come back and check your work. All right, here we go. Final stretch, 2x squared. So I get 2x to the power of 4 plus, look at this, 8x squared. Let's do a subtraction. That's gone. I've got negative x cubed minus 8x squared. And then I've got plus 2x squared here. So I'll bring that in. And I'm going to simplify this first. So that's equal to negative x cubed minus 6x squared in there. Right, so now I'll look for my quotient at minus x. Would you agree? Minus x times x squared is minus x cubed. Minus x times 4 is minus 4x. Now I do a subtraction. I better bring my minus 4x down here, hadn't I? So I've got a minus 4x here as well. So that's cancelled. I've got negative 6x squared. Just keep an eye on things here. Negative 4x minus negative 4x. That's cancelled out. All right, so I've got negative 6x squared. And now I'll bring down my negative 24 into the fray. and I've just got a -6 to run through to get rid of the -6x squared, but magically the -24 gets me back to 0. So that tells me what? That qx is equal to this. So I have refined my work. I have now got that my function of x is equal to x squared plus 4. And take note, what's x squared plus 4? If you'd made that equal to 0 to find your roots, to find your solutions, you would have said, no solution, or no real solution. But x squared plus 4 equal to 0, we're enlightened, aren't we? Yes, x is equal to plus or minus the square root of -4, but we don't write it like that. We write it as plus or minus the square root of 4 times the square root of -1, and the square root of -1 is now equal to I, plus or minus 2i. Hang on a second. It's all coming together. Isn't this beautiful? Okay, so that's one factor. My other factor is 2x squared minus x minus 6. We're almost there, folks. Multiplies to -12, adds to -1. It looks like my old favourite -4 and 3 here to run through this 2x squared minus 4x plus 3x minus 6. All right, so that's equal to 2x x minus 2 plus 3 x minus 2. So that's equal to 2x plus 3 x minus 2. So the final factorized version is x squared plus 4, which is that product of x plus 2i and x minus 2i. And our linears are, it's not that at all, 2x plus 3, x minus 2. And so we can say with no shortage of relief and happiness that the remaining zeros, which is what the question was asking, it was zeros, the remaining zeros of f. Therefore, the remaining zeros are, right, we'd already identified out of this one 2i plus and minus. Now out of here we get -3/2, gives me a 0 here. Negatives and 2. They're my remaining zeros. -3/2 and 2. All right, so here's our quartic that we've just found the factors for, and you can see the real zeros on the screen here. We've got 2 and what's that? -3/2, and obviously we've got 2 complex roots as well that we can't see. So there's our quartic, and I think our work is done. We now need to do exercise 3L here. So if we can do exercise 3L, that would be wonderful. I think the questions from 3 to 6 will benefit us most. So that's it. Cheers.